Hi, I'm Dr. Billy Wu, and in this video I'll be giving an introduction to lithium-ion batteries, covering materials, key metrics, operating mechanisms, industry landscape, and the outlook for the technology. So firstly, let's have a look at why batteries are important. In short, portable consumer electronics such as mobile phones and laptops have been enabled through the ability to store energy in a compact and energy-dense way. The batteries in these devices generally have a capacity on the order of several watt-hours, where 1 watt-hour means you can discharge the battery at 1 watt for 1 hour, or 2 watts for half an hour, or half a watt for 2 hours. Next, there's an increased focus on the decarbonization of transport, where the internal combustion engine is one of the major contributors to global carbon dioxide emissions. In order to address this, many automotive manufacturers are now developing battery electric vehicles, where the battery size is of the order of approximately 10 to 100 kilowatt hours. Finally, we need to decarbonize the way we generate electricity, which goes into these electric cars. Otherwise, we run the risk of pushing the pollution problem elsewhere in the system. Renewable energy sources, such as wind and solar, are a good solution here. However, these are intermittent, and therefore there's a need for large-scale energy storage technologies to help buffer supply and demand. In this application, the energy storage devices are of the order of several megawatt hours. Now, when we talk about battery technologies, there's actually many different types, which we often characterize by their volumetric and gravimetric energy densities. As a point of reference, petrol has an approximate energy density of 9,500 watt-hours per liter and 12,800 watt-hours per kilogram. However, the efficiency of the internal combustion engine is generally quite poor. If we assume this to be 25%, then these numbers drop down to approximately 2,400 watt-hours per liter and 3,200 watt-hours per kilogram, which are still high, however starts to capture the whole system considerations. Now, as we mentioned before, there are a range of different battery technologies, with the lead-acid battery being one of the first commercially available ones. This was initially used to power things like milk floats and is still used today as starter batteries in cars. The nickel-cadmium battery offered an improvement to the energy density of lead-acid batteries, which enabled portable electronics. However, this chemistry was plagued by the memory effect, where if a battery is repeatedly charged before all its energy is depleted, it will memorize the decreased life cycle, and the next time you use it, you may notice a significantly shorter operating time. The nickel metal hydride battery again offered improvements in capacity to the nickel-cadmium battery without the need for toxic elements such as cadmium. This technology therefore found its way into some electric vehicles such as earlier versions of the Toyota Prius. However, the real breakthrough in energy storage technology was with the advent of the modern-day lithium-ion battery, which typically consists of a graphite anode and a transition metal oxide cathode. This technology is the one which is powering your mobile phones and electric vehicles. Now, whilst lithium-ion is well established, many people are also researching next-generation technologies. This includes lithium metal anodes, where we replace the graphite with pure metallic lithium. The challenge here is preventing the major failure mode called dendrite formation, where shards of metallic lithium can cause internal short circuits. Here, solid-state battery technologies are being heavily researched as a solution. Beyond that, we have lithium-sulfur batteries, where the cathode has been replaced with sulfur, which has an exceptionally high capacity and low cost. And finally, metal-air batteries such as zinc-air and lithium-air have long been researched as the ultimate solution for energy-dense batteries, but still suffer from significant challenges. Okay, so let's now focus on the lithium-ion battery and have a look at how this actually works. Here you can see a diagram which represents the cross-section of a cylindrical battery, which you can visualize as having a structure similar to a roll of paper which is connected to the positive and negative terminals. If we then zoom into the cell, we can see it's made up of a number of different layers. First, we have a copper foil which acts as the current collector for the anode. Then we have a porous anode, which is normally made up of graphite. On top of that, we have a microporous separator, which prevents the anode and cathode from touching each other. Then we have a porous cathode, which is made up of a transition metal oxide and a aluminium foil, which acts as the cathode current collector. In each of the porous phases, we also have a liquid electrolyte, which allows for the movement of lithium ions. When the battery is fully charged, lithium exists in between the carbon layers of the graphite. When the battery is discharged, the lithium becomes a lithium ion and an electron. The lithium ions can travel through the electrolyte towards the cathode. However, the electrons have to go around an external circuit where useful electrical work can be extracted. At the cathode, the lithium ions and electrons recombine and go into the layers of the transition metal oxide in a process called intercalation. When charging the battery, the opposite reaction occurs, moving the lithium back into the anode. This back and forth motion thus coins the term rocking chair mechanism, which represents how a lithium-ion battery works. Now, whilst there's been year-on-year improvements to batteries, there still is a need for significant improvements in order to achieve mainstream adoption. One of the key metrics is cost, where the frequently cited number to be cost comparable with the internal combustion engine is $100 per kilowatt hour at the pack level, which means we need a cell cost to be about $50 per kilowatt hour. Currently, this is just over $200 per kilowatt hour at the pack level and just over $100 per kilowatt hour at the cell level, though this varies depending on the volume and application. Next, we need to improve the energy density, which represents the range of an electric vehicle from approximately 250 watt-hours per kilogram to about 500 watt-hours per kilogram. Also, we need to increase the power density, which represents the acceleration of the electric vehicle from current levels of about 3 kilowatts per kilogram to 12 kilowatts per kilogram. However, as we do this, we shouldn't forget about the safety. As we add more and more energy, it becomes more dangerous, and thus there's a need to eliminate the threat of thermal runaway. Lifetime is also critical, especially as we aim to apply these batteries in large-scale grid energy storage applications, and the aim is to hopefully increase the lifetime from about 8 years to 15 years. If we want to electrify more applications, the temperature range over which cells operate must also be improved. And as we manufacture more and more of these cells, we should also aim to improve their predictability and consistency. Finally, as we start to produce many millions of these cells, the sustainability of the system also needs to be considered, with the recyclability generally quite low at the moment, but with a need to move to near 100% recyclability of the materials in the near future. Now, in order to solve some of these problems, it's useful to have a high-level perspective on the battery industry and supply chain. In the first instance, we have the raw materials with key elements including lithium, nickel, cobalt, and copper. Here, where the materials come from can be important, and also how ethically these are sourced. Next, these raw materials are then converted into precursors needed for the active material manufacturing. Here, key considerations include what form of lithium precursor is used, i.e. a lithium carbonate or a lithium hydroxide. The processing method used also is important in terms of the quality of the material produced. Next, these active materials are then mixed and coated onto their current collectors to make electrodes. Here, the manufacturing conditions are critical for good performance. Then, these electrodes are made into cells with different form factors with a resulting formation cycle which can define their future performance. These cells are then taken by Tier 1 automotive suppliers or high-volume automotive companies and made into modules and packs with thermal management systems and battery management systems. Then, these are put into vehicles for the lifetime of their use where the load profile and environmental conditions can define their performance. Then, at the end of life, when a pack has reached 80% of its original capacity, these can either be used in second life applications such as stationary energy storage or be recycled. However, at the heart of a battery is the materials that we use. This can be broken down into three main components. In the anode, the aim is to have a high capacity and low voltage, i.e. to have materials which are to the bottom right-hand side of this plot. In the vast majority of lithium-ion batteries, these have a graphite anode due to the low cost and acceptable capacity of the material. Other types of anode material, such as lithium titanate, also exist. However, these tend to have a lower capacity and higher voltage, which results in a lower energy density. However, there are some high-power niche applications for LTO. An ideal material that many people are investigating is silicon, due to its relative abundance and high capacity. However, the problem is that as you charge and discharge silicon, it can expand and contract by about 300%, which results in pulverization of the material and poor lifetime. The current industry solution is therefore to blend graphite and silicon together to make composite anodes, which is something that Panasonic and Tesla do very successfully. Finally, there's renewed interest in developing metallic lithium anodes, which actually was one of the original battery designs, however, ultimately fell out of favor due to safety and lifetime concerns. Next, we want cathode materials, which again have high capacities, but in this case, we want high voltages, and therefore we want to be on the top right-hand side part of this plot. One of the first lithium-ion battery cathode materials was lithium cobalt oxide, or LCO, which is still used in many portable electronic devices due to their relatively good performance metrics. However, the high cost of cobalt meant that it wasn't really practicable for things like electric vehicles. To address the cost problem, lithium iron phosphate was developed, which is a much lower cost material. However, the drawback is that the capacity and voltage are lower, limiting its performance, though it is still used in high power applications and in recent years has seen renewed interest as there are several system level benefits. Lithium manganese oxide was also a potentially low cost material, however again the performance was less than ideal. This was found in earlier versions of the Nissan Leaf. Then we have the lithium nickel manganese cobalt oxides, or NMC, and the lithium nickel cobalt aluminium oxide, or NCA materials, which are the current state of the art, which automotive companies use. Here, the current trend is to increase the nickel content and decrease the cobalt content to hopefully increase the capacity and reduce the cost. Beyond that, future chemistries are looking to use sulfur due to its extremely low cost and high capacity, and also using oxygen, since this is abundant and effectively free. However, both of these future chemistries have significant lifetime challenges. Then, the final component of interest is the electrolyte, which allows lithium ions to move between the anode and cathode. These are normally organic carbonate compounds with a finite stability window. If a material operates outside of this, it can decompose, leading to a poor lifetime. This can normally happen if a battery overcharges. Now, another feature of interest is that many anode materials are actually outside the stability window of most electrolytes, and therefore it should be unstable. However, we're lucky that in this case, a passivating film forms over the anode called the solid electrolyte interphase, which stabilizes the material, though it does contribute to its long-term degradation. Finally, all of these materials should be cheap, mass-produced, and non-flammable. Failure to achieve one of these criteria leads to limited adoption. Now, whilst both the anode and cathode are important, often the cathode is where the majority of the cost is, and if we look at ideal characteristics we want from the cathode, we can see that we need good specific energy, power, safety, lifetime cost, and for all of these to be in the same device. Again, with lithium cobalt oxide, or LCO, this has a reasonable specific energy, but really the cost was the main drawback. Lithium iron phosphate actually has a whole host of ideal characteristics. However, the main drawback is the specific energy, though the increased safety can have system level benefits to warrant its use. Then the lithium manganese oxide chemistry has ideal cost and safety characteristics, but the lifetime and capacity have meant that this chemistry is rarely used anymore. Thus, the main automotive thrust has been on NMC and NCA, which have ideal specific capacities, but still needs improvements. Here, the move has been towards higher nickel content, where the nickel broadly represents an increase in capacity, the cobalt helps with stability and rate capability, and the manganese helps with safety and cost. Now, as we scale up batteries to the millions needed for electric vehicles, we also need to consider how these are made. In the first instance, we take the active materials of choice and then mix these together with conductive carbon additives, a polymeric binder, and a solvent. The ink is then mixed and coated onto current collectors, after which the electrode is dried to remove the solvent and then calendared or compressed to increase the volumetric energy density. These electrodes are then cut and stacked into the cell form factor of choice, and then the electrolyte is introduced with the cell then being sealed. This has to be done in dry room conditions in order to avoid undesirable reactions. Next, we need to charge the cell, as most lithium-ion batteries are assembled in their uncharged state. This has to be done very slowly in the first instance to form a good SEI, and we term this step of the process formation. Finally, these cells are integrated into a system with a thermal management system and a battery management system. Clearly, there are many steps in this process, and therefore there's still a lot of room for innovation in the battery manufacturing space. Now, if we have a closer look at the performance of different lithium-ion batteries, there are often two key metrics that we often talk about. The first is the C rate, which is the normalized measure of current relative to its cell capacity. Here, you can see that we define the C rate as the current divided by the capacity of the cell. Next, we have the capacity of the cell, which is measured in terms of its amp hours. This is the discharge current multiplied by the time which it maintains this current for. If we look at the example of a 4.8 amp hour cell, this is the discharge curve. Here, if we discharge the cell at 4.8 amps, this is 1C, and this should last for approximately 1 hour. If we decrease the current to 2.4 amps, this is 0.5C, which should last for 2 hours. And if we increase the current to 9.6 amps, this is 2C, and this should last for half an hour. If we expand on what these discharge curves look like in terms of their voltage time response, we get this plot for the three different C rates. Here, higher voltage means that we are at a higher state of charge and have more energy left, and as we increase the current, the discharge time is shorter. However, to have a fair comparison of performance, we should plot this as a voltage against capacity plot, where it's more evident now that the accessible capacity is less and also the losses are higher when we increase the current as the voltage is lower. Now, while C rate and capacity are key metrics, we ultimately care about the energy of the cell, so let's have a look at some battery datasheets to see what information we can extract. Here you can see the performance of a Panasonic 18650 cylindrical cell, which has a nominal or average voltage of 3.6 volts and a capacity of 3.35 amp hours, which gives us an energy of 12 watt hour. Now we can also see that this cell has a weight of 47.5 grams, which then allows us to work out that this cell has an energy density of 254 watt hours per kilogram. On the right hand side, we have another datasheet from a A123 lithium iron phosphate 26650 cell. Here, the nominal voltage is lower at 3.3 volts with a capacity of 2.3 amp hours, giving an energy of 7.6 watt hours. This cell has a mass of 70 grams and therefore gives us a specific energy of 108 watt hours per kilogram, which highlights the fact that LFP has lower energy density than other chemistries such as NMC and NCA. However, again, energy is just one metric, and certain cells such as LFP often have ideal power and lifetime characteristics. In this case, these two examples are of an energy cell and a power cell. Finally, as we briefly touched on earlier, there are different form factors of cells we can get. Prismatic cells generally have a high degree of mechanical stability since they have a rigid case and are often used in applications such as phones. Cylindrical batteries again have good mechanical stabilities and generally are the lowest cost form factor due to ease of manufacturing, with these being used in power tools and many electric vehicles. The most common cylindrical is the 18650, which means that this cell has a diameter of 18 millimeters and is 65 millimeters long. Finally, we have the pouch cell, which in theory has the highest energy density of the different form factors, but has low mechanical stability due to the lack of a rigid case. This is often found in applications such as drones, where the energy density is even more critical. So, we can see that there are many considerations needed to make better batteries. First, we need to make sure we have the right chemistry, and this really is the foundation of performance and cost. Next, we need to optimize its microstructure, which relates to how the particles pack together. This can really define whether a cell has better power or energy characteristics. Cell design also has lots of room for optimization, with cylindrical, prismatic, and pouch cells possible options. And finally, we need to take these cells and put them into a battery pack with a thermal management system, battery management system, and enclosures. Thus, overall, this is a multi-length scale problem which needs innovations in fields ranging from material science to mechanical engineering. So, to summarize, lithium-ion batteries are increasingly more commonplace. There are many different types of batteries which are defined by their anode and cathode materials. With lithium-ion batteries, they work via a rocking chair mechanism where the lithium moves back and forth between the anode and cathode. The key metrics of interest are cost, energy density, power density, safety, lifetime, operating temperature, predictability, and recyclability. The industry landscape for batteries covers many different aspects from mining, chemical processing, electrode manufacturing, cell and pack manufacturing, integration, and recycling. Within the lithium-ion battery space, there is again a variety of different anode and cathode materials, with the most common anode material being graphite, but with a general move to graphite silicon composites and potentially metallic lithium. The most common cathode material is NMC, where the move is towards more nickel-rich chemistries. Key performance metrics include C-rate, capacity, and energy, where we looked at some datasheets and discussed the role of power and energy cells. And finally, we discussed the different form factors, which include cylindrical, prismatic, and pouch cells. So hopefully this video was a useful introduction into lithium-ion batteries, which covered the core principles of how they worked and key considerations across the supply chain. No doubt, in the years to come, there will be continued innovation in these areas, but having a firm foundational knowledge of what's going on in the system will allow us to make more informed decisions.